Okay, guys, let's talk about cylindrical coordinates today. So what are cylindrical coordinates? This is the tool for finding certain triple integrals. And the basis for understanding this kind of integrals is nothing else but the familiar polar coordinates. We will review them in a second, but what did we use polar coordinates so far? You're right, for finding the double integrals. So let's review quickly the double integrals and polar coordinates. So there we had to find a double integral of some over some region, which had some function, which had some kind of rotational symmetry. So it was beneficial to represent it, to describe it in polar coordinates, maybe as a polar rectangle, or maybe as a curved polar rectangle. Maybe something like this. R would be type 1 polar rectangle between, say, R1 of theta and R2 of theta. I'm talking about curved sector, curved circular sector. R1 function of theta, R2 function of theta, and theta is fixed between alpha and beta. Theta is in between alpha and beta. So then in that case, we would write it in polar coordinates. Go ahead and write it in, put the video on pause. After pause, come back and see if you've gotten it right. If that was a function of x and y, then now this would be a still function of x and y, rewritten though as r cosine theta, r sine theta. So in effect, a function of r and theta. And here we have, instead of dA, r dr d theta, correct. And since it's the curved sector, in other words, we are integrating from the inside out, we have the inside limit and the outside limit, definite limits on r as functions of theta. Then the first integration is done with respect to r from r1 of theta until r2 of theta. And then integration theta from alpha to beta. So hopefully that's what you've gotten. Check. And that's the review of double integrals in polar coordinates. So cylindrical coordinates are special coordinates in 3D which allow us to take integrals over solids which have rotational symmetry around an axis. And typically that would be the z-axis. In other words, you will see how such a triple integral of a dv would be written as integral with respect to z first. We're assuming that's so our solid would have some kind of rotational symmetry around an axis, and we'll call this axis z-axis, and it will have a certain top and bottom lid, let's say u2 and u1, and the whole idea is z is u2 and z is u1 as a function of x and y. And the whole idea here is that the rest will be written using polar coordinates. So this all happens on top of the region on the xy plane, so projects nicely into, well, if we are talking about rotational symmetry, now it would be something like a circle, not necessarily the full circle, maybe part of it, maybe an annual region. But okay, let's say for simplicity a disk now. Then first integration will be done with respect to z, as for type 1 solid in general. So that's our first integral dz from u1 of xy, u2 of xy, and then that integral dA, double integral remaining with respect to a, would be written just like in polar coordinates using this conversion rd theta with this conversion factor. So we can eventually write the whole thing as triple integral first with respect to z, u1, u2, and then we have the conversion factor. Let's put it here, r, dr, d theta. So then with respect to r from, let's say, could be curvilinear region. In this case, let's assume it's a disk of radius a, and from 0 to a, and from 0 to 2 pi. Of course, this could be more general or more general. But that's the idea. So let's see what kind of coordinates will we see in this case. So this will be, of course, a straightforward generalization of polar coordinates, where we're just adding z as the third coordinate. But just in case you've forgotten your polar coordinates, let's quickly review. So these are the pair x and y, which are related to r and theta. How? Go ahead and write the formulas for x and y in terms of theta. And then r and theta in terms of x and y. Okay, if you have them, then if you don't put it on pause, if you have them, then check. That's what you should have. This should be equality, of course. So notice that, remember your precalculus, we don't like to write theta explicitly as arctan y over x. Why not? We'll check in the next class. Hopefully you'll remember. Question is, why not just express theta as arctan y over x? If you don't know the answer to this question, go back to Stuart and review your polar coordinates. And we'll move on. So cylindrical coordinates will be versus rectangular x, y, z will be the polar coordinates r theta plus z coordinates is copied, z coordinate is copied unchanged. That's it. So r is x squared plus y squared, and theta is such square rooted. Theta is, of course, such that arctan theta, well, we don't like arctan, so we'll say tan theta is y over x. So that will help us deal with certain triple integrals. We'll discuss triple integrals in a few minutes, but let's get comfortable with cylindrical coordinates first. So you can think of cylindrical coordinates as taking a point in space, projecting it onto the xy plane. You'll get this point, then assigning r and theta polar coordinates to it, and then adding the z coordinate of the original. Okay, so in practice, these are the conversion formulas, of course, one way or another. Given the cylindrical, this is the way to convert to rectangular, x, y, and z. Given rectangular x, y, z, that's the way to convert to cylindrical. Again, we don't like to express theta explicitly because we may have to have an adjustment of pi. Right? Arctangent doesn't give us the whole story. It only gives us what happens from negative pi over 2 to pi over 2, but you have to plot a point and see if the point is somewhere in the second quadrant, then you have to take your arctangent and add or subtract a pi to it. So if this was arctan y over x, then maybe you need to add or subtract a pi. if your XY point is plotted in the second quadrant. Okay, so let's take a look at some examples. First, we want to plot a point with cylindrical coordinates 2 to pi over 3 and 1. Okay, how do we do that? And we want to find its rectangular coordinates after we plot it. Well, we have to realize that if it says cylindrical coordinates, that r is, it means that r is equal to 2, theta is equal to 2 pi over 3, and z is equal to 1. In other words, let's start with xy coordinates first. R is equal to 2 just means that we are in this polar grid 2 units away from the origin. But in which direction? Well, we have to count 2 pi over 3 along this circle. R is equal to 2. So we have to count 2 pi over 3 in the counterclockwise direction. So pi over 2, 2 pi is too much. 2 pi over 3 is 120, right? So somewhere here, this is 2 pi over 3. So we ended up in the second quadrant. Now that means that our x and y will be r cosine theta, r sine theta. So we have 2 cosine of 2 pi over 3, cosine of 120 is negative 1/2, so 2 times negative 1/2 is negative 1. Our y is 2 sine 2 pi over 3, that is root 3 over 2, and that will give us root 3. All we have to do now is to add the z coordinate. Z is equal to 1 unchanged. So how do we plot it? Maybe we should have started with that. So, well, we started by plotting it in xy. So how do we reproduce it in 3D? Well, in xy, we will go to, again, this is first circle, the second concentric circle. So we have to go to 2 pi over 3. So we're going along this way. We ended here, with 120 degrees, and then we're going up 1 unit along z. So that is the point with coordinates 2 to pi over 3, 1 understood as its polar coordinates. Done with that. Any questions? Did you get the same? So again, try to figure out the second one. Now you have to convert from rectangular to cylindrical. So rectangular 3, negative 3, and 7. So that means that if x is 3, y is negative 3, then r will be square root of 3 squared plus negative 3 squared. What do you get? Square root of 18, or 3 roots of 2. Okay, so if that is your r, again, let's start with xy picture. What is your theta? So the point itself is 3, negative 3. So if this is 3, y is negative 3, we're here. We're in the fourth quadrant. So that is the point, that is the angle. Well, if you allow negative angles, negative pi over 4, or for talking for positive angles, or maybe I should draw it to the point. So then you would have 7 pi over 4 angles. So we can say theta is 7 pi over 4. I guess the standard one, if you're considering 0 to 2 pi as the standard range. So theta could be 7 pi over 4 or negative pi over 4, or most generally start with the standard representation and add any number of 2 pi's times k. So k is any integer. Okay, so for instance, we can give it 3 root 2 and 7 pi over 4. So we've gotten the xy coordinate. The z coordinate is just unchanged. Z coordinate will be same as here. So z will be negative 7. So this will convert to cylindrical as cylindrical 3 root 2, 7 pi over 4, or any one of those, and -7. Good. Let's take a look. That's the first example, and that is the calculation of the rectangular coordinates, and that's the second example. And that's the calculation of the rectangular coordinates, rectangular two polar. So we've gotten the polar, cylindrical, I should say, coordinates of 3 root 2, negative pi over 4, or 7 pi over 4, and -7. Good. But there are infinitely many choices. So for instance, we can write another choice. If we go even further negative, add another 2 pi. So 8 pi over 4, so 8 minus 9 pi over 4. 3 root 2, 7. So infinitely many choices here. Good. So now that we're hopefully comfortable with the coordinates themselves, let's evaluate some triple integrals with cylindrical coordinates. So what triple integrals? As I said, whenever there is some kind of cylindrical rotation, symmetry, so symmetry with respect to rotation about an axis. And this axis will be a z-axis. And also pay attention to the function. If the function inside the integral involves, so either cylindrical coordinates are useful for first rotations, so rotations around an axis, So if you have rotational symmetry around an axis, and second, if your function involves factors of x squared plus y squared. So that's clear sign of, okay, try to change it to r squared and proceed from there. So let's see. So here maybe rotational symmetry is not obvious at all unless you look at the image, at the projection on the xy axis. But what do we see here? We see the typical type 1 solid, where you have well-defined top and the bottom limits, top and the bottom lids of your region as functions of x and y. So you probably will integrate it with respect to z first, and then look at the region in the xy plane, dA. Look at this region D. So you integrate with respect to D between these two top and the bottom limits. So from the bottom limit u1 of xy to the top u2 of xy. But then you look at the bottom region, you realize, okay, it looks like a curved linear, circular sector, almost like a polar rectangle, except the top and the bottom limits are not constants. They would be constants, that would be a perfect polar rectangle. This way it's a curved circular sector, and that's convenient to take in polar coordinates. So polar coordinates in the xy plane together with z means that you're dealing with cylindrical coordinates here. So that's the typical scenario. And we will calculate such a typical case in a second. So then that's how you will approach it, and then use the polar coordinates here to rewrite dA as r dr d theta. So altogether you will end up with r dz dr d theta. So that's the conversion of your volume element. So dV is known as volume element. And that's how it converts. That's the conversion factor, same as with polar coordinates for double integrals, R conversion factor. And the visual to remember that is just the way that you would chop this solid into pieces will be like that. You will chop it along the polar coordinates on the bottom, and you just add dz in the vertical direction. So you will have, if this is r, this is dr, and this is d theta, you will have this side equal r d theta. That side is, of course, dr, and that side is dz. dr and dz. So that's why you will write it as typically r dz dr d theta for the situations that we discussed. But there could be other situations as well. What if you have the region rather than curved circular sector? You could have something like this, region of type 2 in the plane, in the x, y plane. Then you would maybe switch r and theta, the r and the theta places. Okay, so let's take a look at the concrete example. So in general, all you have to do to finish the problem is then convert everything in terms of r, theta, and z. So the most important part is converting the volume element with this conversion factor, but also you have to substitute everywhere the formulas for rectangular in terms of cylindrical coordinates. So here, there, everywhere. Now you convert it to cylindrical coordinates. That's the formula for integration in cylindrical coordinates. So that's the quick mental check if you forgot how does the volume element convert. And how do you know if you should use it or not? Well, if you see x squared plus y squared, then maybe inside the integral, then maybe it's a candidate for the conversion to cylindrical. If you see x squared plus y squared plus z squared, then that would be the next kind of coordinates that we'll be discussing. Spherical coordinates where you would rotate around the point rather than around the axis, around the z-axis. So now you know when to use what. So here's an example. We want to calculate the mass of this solid, and the solid is within the cylinder, but below z equals 4 plane, and above the paraboloid here, z equals 1 minus, think about it, x squared plus y squared, this paraboloid. So above paraboloid, under the plane, and within the cylinder. So how do we use the cylindrical coordinates here? Well, let's set up the bounds for the region. Let's describe the region. So we can describe the region in cylindrical coordinates. So since it's inside the cylinder, the projection onto the xy plane will be just a circle, right? Will be just a unit circle. So that is r equals 1. So clearly, we will be doing the integration on top of this unit circle. And also, we do have the type 1 region, right? Because we have definite bottom lid, definite top lid here. So these are the top and bottom limits. So we'll start with the integration with respect to z, like that. So that will be our first integration. So triple integral. Notice we haven't said anything about the function yet. but we can set up the region, the integral over the region already. So the first integral will be with respect to z from the bottom limit, 1 minus x squared plus y squared, until the top limit of 4. What's inside? Well, we'll discuss it later. And then double integral over the disk. But the disk is simple thing, so dr d theta. Or maybe at this point you think it's r dr d theta. So that's when you remember the conversion factor if you didn't remember it from the beginning. So r dr d theta, and r lasts from 0 until 1, perfect polar rectangle, and theta will be from 0 until the 2 pi. So we set up the solid, the integral over the solid. Now what are we integrating? Since it's supposed to be the mass of the solid, then we'll have to integrate, you tell me. Right, density, but is the density given explicitly? No, it just says that the density is proportional to something, to what? To the distance from the axis of the cylinder. Okay, what is the axis of the cylinder? Z, of course. What is the distance from a point P with coordinates x, y, z to the z-axis? Well, we can project the whole situation in the xy plane, and we can see that it will be x and y will matter, and z not so much, right? Because z doesn't change. So the distance, this distance d, will be nothing but square root of x squared plus y squared. Okay, and that is what our density is proportional to. R is proportional to this distance to the z-plane, to the z-axis, square root of x squared plus y squared. Okay, good. So then what does it equal then? It follows that density should be exactly equal to what? Right, if it's proportional to a quantity, then it will be a constant, call it k, times the quantity itself. In other words, it will be k square roots of x squared plus y squared. So if that's our density, we'll just plug it in to the integral, and we will have here, instead of dot, 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 we will have here k, which we can take outside. We can write it here as k. And notice that in polar coordinates in the xy plane, this is just kr. So we can just put here r. We can just put here r. So as a result, let's now start integrating. Maybe before, let's take another look at this integral and see if there are any questions. Is that what you've gotten when you paused the video earlier? So if yes, then let's proceed. First integration with respect to z will give us just, because r squared is a constant, we can take it outside. R squared is a constant. Integration with respect to z will give us z evaluated at the top. We'll get 4. At the bottom, we'll get 1 minus r squared, because that was 1 minus r squared. So that's the first integral. After that, we do integration with respect to r, and then with respect to theta. So we will get k 0 to 2 pi integral with respect to theta, 0 until 1 with respect to r. What are we integrating? We had 4 minus 1 is 3, so we'll have 3r squared if we distribute, and plus r squared. If we multiply by r squared, we'll get r fourth, dr d theta. So as a result, we'll get r cubed as an integral plus r fifth over 5 between 0 and 1. And finally, k times the integral from 0 until 2 pi of this gadget. Let's clear up some space. And we will have This internal integral, of course, does not depend on theta, so we can just multiply it by, take it out, that would be a constant, and multiply it by 2 pi, integral from 0 to pi of 1. And what do we have in parentheses here? We can just plug in 1. That's the only contribution. On the bottom, we have none. So we have 1 plus 1/5. We'll get 6/5 to pi k. So 12 pi k over 5. That's what I got. Let's see if it's correct. It all out. Or if I made a mistake, hopefully you caught it. So that's the density. From the description, from the variable description, we plug it in, we set up the solid as we discussed. We have the internal integral. We do the integration, that's what we get, 12 pi k over 5. All right, that's all for today.